So, before we move on to the postulates of quantum mechanics, let's do a little math review. So we're going to talk about complex numbers because that's something you're going to see a lot in quantum mechanics. So, what's the square root of -1? What number you multiply by itself gives you -1? No such number, right? It's not a real number. So we just imagine that there is such a number. So we call that number an imaginary number I. So if you take I squared, you get -1. Okay? So I, then we say the imaginary number I is the square root of -1. Now, a complex number is defined as a sum of a real number plus a real number times I. So that's the definition of a complex number. In other words, here's another way of thinking of a complex number. It's just a number it's just a pair of numbers. Okay? One by itself and one that's multiplied by the square root of -1. So we say that if z is a complex number, then z, a right here, is the real part of z. Okay, so that's how you write, that's what that notation means. And b right here, the number that's in front of the I, is the imaginary part of z. Okay, geometric analogy for this is think of a real number as a point on a line. Okay, you just need one number to specify. Once you specify your origin, you just need one number to specify a location on the line. So a number is a point on a line, whereas a complex number is a point on a plane. So if you have a plane, okay, any point on the plane, you need two numbers to specify its location, right? You need the x-axis, right? The value along the x-axis and the value along the y-axis. So we can, if this is A and that's B, okay, then a point on the plane would correspond to a complex number. Okay, so you need two real numbers to specify a complex number. So you can think of the x-axis then as the real axis, okay, or whatever your number is, and your y-axis as the imaginary axis of your complex. The plane is called a complex plane. So, given that z is 3, suppose z is 3 minus 2I, what's the real part of z and what's the imaginary part of z? What's the answer to this one? The real part of z is 3, right? So it can't be this. And the imaginary part of z is -2, the number that goes with 2, with I, so 3 and -2. How about this one? True or false? A real number is also a complex number. True. Okay. So how can a complex number be a real number? So if z is equal to a plus bi, how can this z be a real number? If b is 0, right? Then z is real. Okay. If z is 2, what's the imaginary part of z? Z is 2, that's a real number, right? So you can say z is 2 plus 0 times I. So the imaginary part of z is 0. Okay. Let's define complex conjugate. So if z is a complex number given by a plus bi, then its complex conjugate is obtained by replacing I by -I. So if z is a plus bi, I'm going to the complex conjugate, I represent that by z star. I simply replace I by -I. So I'm just going to say that's going to be a plus b times -I, which is the same thing as a minus bi. Okay, so if z is 2 minus 3i, what is z star? 2 plus 3i. So you say 2 minus 3 times -I. Anytime you see an I, replace by -I. So that's 2 plus 3i. Did I record this? Yeah, I did. Okay. All right. So z is -5. What's the complex conjugate of z? So z is negative 5 plus 0i. So z star would be negative 5 plus 0 times negative I, which is still going to be negative 5. So in other words, if z is equal to z star, what does that tell you? You're dealing with a real number. Okay? So z is a real number if its complex conjugate is equal to itself. Which of the following is not equal to the other three? So three of these things belong together. They're kind of the same. Which one's not the same? Okay, let's do I star. You see a star, you replace, anytime you see an I, you replace by negative I. So this is the same thing as negative I, right? So A and B are the same. What about 1 over I? Let's try B first, that's easier. What's I star times I? I star is negative I, right? And that's I. So what's negative I times I? Negative I squared. What is I squared? I is square root of negative 1, so I squared is negative 1. So negative of negative 1, so that's going to be, so D is not like A and B, so it's got to be D, right? So this is the one that's different. This is equal to 1, right? What is 1 over I? How is 1 over I equal to these? 1 over I, multiply both numerator and denominator by I over I. What do you get? I over I squared, right? Which is I over, what is I squared? Negative 1, so that's negative I. Okay, so C, A, and B are all the same. And these are all the same. Okay. Another way I could have done this is I could say 1 over I times I, never mind. That's the easiest way to do it. Okay. What about this one? If Z is A plus BI, and its complex conjugate is Z star, is A minus BI, right? Then we define the square of its absolute value as Z star times Z. And the square root of Z star times Z is the absolute value of Z. Okay, so let's apply that definition. What's the absolute value of 1 plus 2i? So let's write Z star. Z star is 1 minus 2i. So what is Z star times Z? 1 minus 2i times 1 plus 2i. Sum and difference. What is A minus B times A plus B? A squared minus B squared, right? So here you have 1 squared minus 2 squared. 2i squared, right? Okay, see, this is A minus B. This whole thing is B, okay? A plus B. So what is 1 squared minus 2i squared? What is 2i squared? 4. That's 2 squared, and then I squared, right? So that's 1 squared minus 4 times, what is I squared? Negative 1. So this is just 1 plus 4. So that's 5. Okay? So in general, okay? In general, if Z is A plus BI, then you can say Z star Z is just A squared plus B squared. Right? And so what's the absolute value of Z? The square root of Z star Z This is the square root of a squared plus b squared. Plus. When referring to this b right here, we call b different here. So if you don't, to avoid confusion, let's just call this x plus y, x minus y, and x plus y. Okay, since we've already defined a and b here. Okay, so a squared plus b squared. It's square root of a squared plus bi minus bi squared. See, a squared minus bi squared. But I squared is -1, so that ends up being a squared plus b squared. You got it? Okay, so let's look at this thing right here, this example. What is the absolute value of 1 plus 2i? Absolute value of z would be square root of 1 squared plus 2 squared square root of 5. Okay? So if z is equal to 4 minus 3i, what's the absolute value of z? Square root of a squared plus b squared, which is -3 squared, square root of 16 plus 9, square root of 25. Okay? Does that formula look familiar? Looks like a Pythagorean formula, right? A squared plus b squared is equal to z squared. All right. So if z is -5, what is z star? Also -5. What is z star times z? -5 times -5, positive 25. Z star times z is always a positive real number. What's the absolute value of z? Square root of 25 is 5. So absolute value of z is always a positive number. So it applies, and you could have done that without knowing about complex numbers, right? So the definition that we're using for absolute value of a complex number is consistent with our definition of complex number for real numbers. Okay? If z is -5, you know absolute value of z is just positive 5. All right. So here's a geometric analogy for absolute value. So remember you said a complex number can be represented by a point on a plane, the complex plane. So the x coordinate is the real part of z, right? And the y coordinate b is the imaginary part of z. So this is a and that's b. So what is the square root of a squared plus b squared? This is a right triangle, right? So that's just the hypotenuse. So the absolute value of z is really just the hypotenuse. Right? It's the distance from the point to the origin, from the point on the complex plane that represents that number to the origin. Okay, so absolute value of z is just the length of the hypotenuse, the line from 0, 0, actually the line segment from 0, 0 to point AB. Now, that suggests then that there's another way of representing a complex number. Okay, instead of using a and b, the imaginary and real components, okay, you can define an angle theta from the z-axis to this line that connects the origin to your point. So let's call that theta. Okay. Then what is a? Sine theta. What is sine theta? Sine theta is opposite over hypotenuse, right? So it's b over absolute value of, this is absolute value of z. So b is just absolute value of z times sine theta. Right? And you should easily show, should be able to show easily that cosine theta is what? Adjacent over the hypotenuse. So it's going to be A over absolute value of Z. So A is just absolute value of Z times the cosine of theta. So you can rewrite our expression A plus BI. Instead of writing, so this is Z, you say, is A plus BI. So A is absolute value of Z cosine theta, plus B is absolute value of Z sine theta times I, right? So what can we do? We can factor out absolute value of Z. And what do you have inside? Cosine theta plus I sine theta, right? So cosine theta plus I sine theta, right? This one right here. Okay? Now, you can show that cosine theta plus I sine theta is just e to the I theta, or exp to the I of I theta. So you can also rewrite this as Z is equal to absolute value times e to the I theta. Or I can write it down. So that's an alternative way of representing a complex number. You represent it by the magnitude and the angle that you have to sweep from the x-axis to get to that point. So the magnitude and the phase, PHASE. Okay. So this expression right here, e to the ix, is equal to cosine x plus I sine x. That's called the Euler formula. Okay, you're going to encounter that a lot in quantum mechanics. So, and here's a couple of identities that you should be very familiar with, because you're going to encounter this a lot. Just to give you a heads up, when we get to atomic orbitals for, you remember your quantum number m plus 1, 0 plus 1 minus 1 for p orbitals. If you take combinations of those, you get your px and your py orbital. So we'll get to that later this semester. But anyway, cosine x can be shown to be 1/2 of e to the ix plus e to the minus x. I'm going to show this, and then this is going to be your homework. Okay? And starting today, no more late homeworks will be accepted. Okay? So let's do cosine x. 1/2 e to the ix plus e to the negative ix. How can I show that? Well, let's see. 1/2, what is e to the ix? By definition, that is what? Cosine x plus I sine x, right? What is e to the negative ix? That's the same thing as e to the I times negative x, right? So that part right there is cosine of negative x plus I sine of negative x. Okay? So what can I do to simplify this expression? What is cosine of negative x? That's just cosine x. Cosine is an even function. What is sine of negative x? Negative sine x. So this is negative I sine x, right? Oh, I put the I here. And this is negative sine x. So what happens here? What can I cancel? I can cancel I sine x and negative I sine x. So that gives me 1/2 times 2 cosine x. And what's 1/2 of 2 cosine x? Cosine x. Okay? So important thing to remember here that e to the ix is cosine x plus I sine x. You can also say that e to the negative ix is cosine x minus I sine x. So your homework would be to show that sine x is 1 over 2I times e to the ix minus e to the negative ix. Yeah. Where x can be anything, okay? E to the I anything is equal to cosine anything plus I sine anything. That sine x, the second one, the second identity right here. We just did the first one. We just showed that 1/2 of e to the ix plus e to the negative ix is cosine x. So you need to show that sine x is 1 over 2I times e to the ix minus e to the negative ix. Question? No. Alright. Suppose z is equal to e to the negative I pi over 2. What's the real part of z? What's the imaginary part of z? And what's the absolute value of z? So you can see that this is the absolute value of z, e to the I theta, right? So what is our absolute value of z? It's 3. What is our theta? Negative pi over 2. So where would that be on the complex plane? Negative pi over 2, you go down 90 degrees, right? And so this is negative pi over 2, right? And how far away from the origin are we? 1, 2, 3. Okay, so that's at negative 3. So what's the real part of z? Zero, right? Okay, so z is 0 plus negative 3 times I. The imaginary part is negative 3. What's the absolute value of z? It's 3. Okay, what if z is 3 times e to the negative I pi over 2, what is z star? Anytime you see an I, replaced by negative I. So this is going to be 3 e to the negative of negative I pi over 2. Okay, that's how you take a complex conjugate. Every time you see an I, replaced by negative I. So that gives you 3 e to the I pi over 2. So where would that be on your complex plane? Remember what did we say this one was? It's this one right here, right? This is negative pi over 2. So if you want to go this time to theta, this time is positive pi over 2. So that's positive pi over 2. So 1, 2, 3. So complex conjugates are just mirror images across the x-axis. Why is that? Remember, you do a plus bi and a minus bi. Okay, you're just changing the imaginary component. If the imaginary component is positive, the complex conjugate will have a negative imaginary component. Okay, if the imaginary component is negative, then the complex conjugate would have the opposite imaginary component. Okay, so that's your z star. Okay, so which of the points represents the complex conjugate of z if z is 2 minus 2i? Where is 2 minus 2i? That's 2 and negative 2, so here's z right here, right? That's 2, 1, 2, negative 1, negative 2. That's your z. Where is z star? 1a. Okay? It's going to be 2, positive 2, right? It's going to be 2 plus 2. Alright, what about this one? if z is equal to 1 over 2 plus 2i, what's the real part of z and what's the imaginary part of z? The trick here is to make this look like a plus bi. What is a and what is b? The real part of z is a, what is it? And the imaginary part of z is b, what is it? What you need to do is, it's just like getting rid of square roots in the denominator. You rationalize it. So you multiply this by 2 minus 2i over 2 minus 2i. Because what happens when you multiply this by its complex conjugate? Anytime you have a complex number, you multiply by complex conjugate, you get a real number. So that gets rid of the I in the denominator. Okay, homework number 2. Okay. Let's talk about the complex conjugate of a function. If f is a function of x, okay, then the complex conjugate of function f is obtained by simply replacing all instances of I by negative I. So that's the rule. To take the complex conjugate of anything, anytime you see an I, replace by negative I. Okay? And now if it's possible for x to be a complex number, then anytime you see an x, you replace it by x star. If you don't know if x is a real number or not, but it could be complex, then anytime you see an x, replace it by x star. Now, if you know x for sure is real, then you don't have to replace it by x star, because if it's a real number, x would be equal to x star. Right? So let's say f is ix over 3 plus 2i. What's the complex conjugate of that? It's going to be, you see an I, replaced by negative I. You see an x, replace it by x star. You see a 3, that's a real number. Complex conjugate of 3 is also 3. 2 is a real number, and replace I here by negative I. Okay? So every time you see an I, replace by negative I. Every time you see an x, replace by x star. Now, what if x happens to be real? Then what do you do? If x is real, then you say f star of x, in this case, would be equal to negative I x over 3 minus 2i. I don't have to put a star on the x. Okay? If I know for a fact that x is real. Okay. Here's where you can show Euler's formula that e to the ix is equal to cosine x plus I sine x in terms of the series expansion, power series expansions of e to the x, cosine x, and sine x. Okay? So let's do, for example, e to the ix. What would it be? Using this, 1 plus, instead of x, I'm going to write 1. Ix plus, instead of x squared, I'm going to write ix squared over 2 factorial. Okay, instead of x cubed, I'm going to write ix cubed over 3 factorial, and so on. Okay, and you should be able to show that e to the ix is equal to cosine x plus I sine x. Okay, so homework number 3. This is kind of easy to show, actually. Look at this. This is all even powers. Cosine has all even powers. Remember, cosine is an even function. And your sine x all has odd powers of x. Okay, so anytime you replace x by negative x, you get the negative of the original function, if it's an odd function. So that's it. And there's some videos on YouTube that explains all of this. If you want more review, I think that should be sufficient review for this. Okay. and Appendix A2, Section A2.2 in your textbook, Atkins.